Hello, everyone. My name is Aska Nadeem. I'm a third-year PhD candidate at Delft University of Technology, and this work was done in collaboration with Dr. Ferrer from Delft and Stephen Moskal and Dr. Yang from Rochester Institute of Technology. In this work, we propose to use cybersecurity data such as intrusion alerts to automatically construct attack graphs for attacker strategy comparison. This is important because we know that security analysts in SOC environments receive thousands of alerts on a daily basis. Some companies have even suggested that they receive more than 1 million alerts each day, which is an insane amount of workload, and it leads to fatigue and reduced productivity. This is also a huge problem because attacker strategy identification is still largely a manual process. After a security incident happens, security analysts want to know how did an attack happen, were multiple attackers involved, and if so, how much of their strategies were similar. These attacker strategies are typically represented in a graphical format called attack graphs. So if we look at what already exists specifically for attack graph generation, surprisingly, we do not find much literature. We found two tools that are used repeatedly, NetSPA, which was a PhD thesis, and Mulval, which was presented at Usenix. They both take network topology and existing vulnerability information as input, which is not feasible if the network is too big or if zero-day vulnerabilities exist, for example. So these techniques use a whole lot of expert input. There are also alert-driven approaches for attack scenario modeling. Notably, Ning et al. Use alert correlation to first group alerts from the same attack stage, and then use some form of causality to model attack scenarios. The Alvarenga et al. Use process mining directly on intrusion alerts and build a sort of visual summary of the alert dataset without actually extracting attack graphs. And then we have Moskal et al. They first construct attack sequences from intrusion alerts and then model the strategies using suffix-based Markov chains, but again, without actually extracting targeted attack graphs. We take initial ideas from Moskal et al. And attempt to answer the main research question, which is how to construct attack graphs directly from intrusion alerts, such that we can extract intelligence about attacker strategies, and preferably building these attack graphs without too much dependence on expert input and network topology. The slide here shows what we are aiming towards. An alert-driven attack graph is a targeted attack graph and is generated on a per victim per objective basis. It shows all the different ways the same objective can be obtained. The attacker actions are shown as vertices. The first action in a path is highlighted so that an analyst knows where an attack actually starts from. It shows all the attackers that obtain a particular objective, so this makes attacker strategy comparison easier. And finally, it also shows time progression in the form of timestamps. But before we can construct these attack graphs, there are two main design challenges that we need to address. The first one being that there's a huge imbalance between severe and non-severe alerts. The severe alerts are infrequent, but they're very interesting from an analyst point of view. On the other hand, the scanning events occur very frequently, and because of this, they are not so interesting for analysis. However, we cannot discard the frequent ones either because, well, they're part of the story. So we need a way to highlight the infrequent severe alerts without discarding the frequent ones. And this is a challenge because most machine learning techniques would simply discard the infrequent events. Second, the same alert can have a different meaning depending on when it happens. And this is what we mean by context modeling. Whatever happens before or after an alert also holds importance, and we need to model it somehow. So in this work, we proposed SAGE, which is an unsupervised sequence learning tool that mines patterns from intrusion alerts. The pipeline itself is pretty straightforward. It takes intrusion alerts as input, converts them into episode sequences pertaining to the different actions. These sequences are used to learn a suffix-based probabilistic deterministic finite automaton. This model is mainly responsible for accentuating severe alerts and for modeling context. Then the sequences are replayed through the SPDFA to enrich them with the context. And finally, these sequences are transformed into a graphical format, turning them into alert-driven attack graphs. So let's go in a little bit of more detail. We start with aggregating alerts of different types into episodes or actions, because one action can result in many, many alerts. So we basically group bursts of alerts together. This step basically converts alerts into episode sequences, which are basically groups of alerts that occur between a particular attacker-victim pair. In addition, we split each attack attempt into separate subsequences because we want to model strategic similarities of each individual attack attempt. Then we give these episode subsequences to the FlexFringe automaton learning framework, which learns the suffix-based probabilistic deterministic finite automaton. This model essentially summarizes all the attack paths present in an alert dataset. The reason why we learn a suffix-based model is because, well, there are only so many severe episodes, so we put them at the top and we predict all the ways in which you can reach these severe episodes. This ends up highlighting the infrequent episodes. In the model here, the color of the states represents the severity of the episodes. So you can see that the severe ones are at the top and the non-severe ones are at the bottom. Each state can be considered as a milestone reached by an attacker. Episodes that have statistically different futures or past are considered different, even if they have the same attack stage. This is what we mean by context modeling. Basically, episodes with different contexts are considered as different states. Then we utilize SPDFA to construct attack graphs. Essentially, we replay the episode sequences through the model and we enrich the sequences with the context, which is denoted by the state identifiers. These state sequences form the attacker strategies, and we represent them in a graphical format, which turns them into alert-driven attack graphs. We construct these graphs on a per victim and per objective basis. So this is how SAGE works. For the experiments, we utilize intrusion alerts collected through the Collegiate Penetration Testing Competition from 2018. This dataset consists of 6 student teams who target a common fictitious network. The competition lasted for 9 hours, producing over 330,000 alerts. Also, instead of using the default Suricata signatures, we use an existing action intent framework from Moskal et al. This is a mapping based on the MITRE attack framework, and it provides a better categorization of the different attack stages. So what do we find? Well, the most obvious benefit that SAGE provides is alert triaging. SAGE compresses over 330,000 alerts in just 93 attack graphs. Each attack graph compresses around 500 alerts in less than 25 vertices on average. So this means that instead of analyzing millions of alerts, analysts can triage alerts based on the attack graphs of interest. The alert-driven attack graphs show how an attack transpired. For example, this is an attack graph that shows 3 teams successfully exfiltrating data from a given victim machine. 2 of the teams make 2 attempts to exfiltrate data, while 1 team only makes a single attempt, producing a total of 5 paths. The SPDFA discovers that there are 3 ways to reach the objective, depending on the paths that lead up to it. The attack graphs also allow strategy comparison. For example, here we see that team 5 and team 8 share a significant portion of a strategy. In addition, some paths are shorter than the others. For example, the green team, team 5, makes 2 attempts. This is the first one, and this is the second one. The second attempt is much shorter than the first. The first one had 12 actions, and the second one has only 8 actions. This trend is seen in other graphs as well. In fact, attackers follow a shorter path to re-exploit an objective in 84.5% of the cases. In this way, alert-driven attack graphs provide insights into attacker behavior dynamics. Finally, we can also rank attackers based on the uniqueness and the severity of the alerts they raise. We propose a simple metric based on weighted average percentage, and we see that team 5 is the most high-profile team, while team 2 visits the least amount of severe vertices. This is different from simple alert counting because we take the context of the actions into account here as well. Also, there is a slight possibility that team 2 is stealthy enough to bypass the intrusion detection system and has still managed to obtain the objectives, but it seems unlikely. In any case, this metric only measures what it can observe, and it basically provides a simple way to rank attackers based on the different ways they find to reach severe vertices. So in conclusion, SAGE uses an unsupervised sequence learning approach to extract attacker strategies. It builds attack graphs directly from intrusion alerts without any expert input, which is great news for security analysts. The SPDFA plays a critical role in highlighting infrequent patterns and for modeling context. The alert-driven attack graphs unlock a new way to extract and analyze attacker strategies. They represent millions of alerts in just a handful of attack graphs, and they provide actionable insight into attacker strategies and into attacker behavior dynamics. Thank you for your attention. SAGE is open source and it's available as a Docker container, which makes integration really easy. So do check it out. And I look forward to answering any questions you have during the workshop.